right. Hello, everyone. Welcome to AWS Made Easy, episode number 78. We're so happy to be joined with Mike Thompson, who's Senior Product Manager at AMD. Let's all unmute our mics. I'm sorry for that confusing music at the beginning. I had made the new countdown, and I realized I had both the jazz track and the Vegas track. And so you had a double bit of music. So sorry about that. That was a bit hard to parse, but now we're all here. So, Mike, welcome. Thank you so much for joining us today.
Good morning, good afternoon, good evening, Stephen, Rahul, and everybody watching. Appreciate you having me.
It's an absolute pleasure to have you here, Mike. Why don't we kick it off with just giving us an introduction about who you are, what you do, and how did you come to be at AMD and work with AWS?
Yeah, well, I'm an engineer by study and by trade. I spent the first part of my career doing chip design. So both ASICs and FPGAs, if you know those acronyms, with ASICs being write once, huge upfront cost, and FPGAs being write as many times as you want, with very little upfront cost. When I came into the industry, I was really interested in helping make an impact on the world. And when I first came into the industry, that really centered around making the internet ubiquitous, and in particular, making Ethernet, which is a communication standard, also ubiquitous. So spent a long time doing chip design for communications, and then started branching out into other things. Maybe the most interesting project I worked on was I lived out in Hawaii for a few years, and there was an opportunity to work on an astronomical telescope camera that was really fascinating. It's maybe the most palpable, the most tangible work output of any of the designs that I've worked on. That camera took the first pictures of planets outside of our solar system. And, you know, for something like that, that's really tangible, where if I go to mom or a cousin and say, hey, I did this chip that does a squillion phone calls per second or a squillion internet phone calls per second, that's not really tangible. But to say, hey, look what's outside of our solar system and actually be able to see it, that's probably the most tangible thing I've worked on. And that really had an impact on me to think, okay, what can I do with my engineering to do something good for the world, or to have more of an impact on tech and the advancement of it? And so after some time, I thought, well, as an engineer here doing chip design, maybe I can work on 1 or 2 projects a year. And I just wanted to be able to touch more projects. And so decided to become a field application engineer, helping customers implement FPGA designs. And that was a fantastic chance to work on so many cool applications, from networking to core infrastructure to graphics and video, storage, life sciences, high frequency trading, financial services, that sort of thing. So that was really fascinating.
Well, I definitely want to ask you a little bit more about the FPGAs. I mean, those are so cool. I've always wanted one of those development boards where you can. So the idea is basically like you can design your own logic layout that runs at basically processor speed, right? But then it's custom designed. You can use it for, I don't know, decoding your own codecs or encryption, or what do people use FPGAs for?
Well, it gets used for all sorts of applications, but particularly for bleeding edge technology before it's really commoditized. For some of those functions, you can buy an off-the-shelf chip that does something very specific, and that would be an ASIC, which has essentially one purpose with a little bit of flexibility, but really it's one purpose. Where the FPGAs are really good is before the merchant silicon or the commoditized silicon is available, because you can write your own logic and it's very, very efficient. It's still an application specific or a custom piece of logic, lots of pieces of logic, but you can do so flexibly, and you can do so without the, say, 1 to 3 year lead time that you need for write once chips like ASICs. And so they get used for everything I mentioned, although frequently they're used for the latest and greatest core telecommunication technologies. So multi-terabit fibers that go under the ocean between different continents. They get used an awful lot for high frequency trading. And because those accelerators are highly customizable, they can get crazy high performance. I've seen some instances where there was an ML model that was used for doing what's called patient outcome prediction, where a doctor can sit down with a patient and look at some certain set of symptoms and then go into this ML model and say, okay, for all the other patients that we've had that have had this certain condition, this certain malady or whatever, and the courses of treatment, to see what were the most effective and what were the most positive outcomes. And in one of those applications, I saw the ability to increase the efficiency of the compute there from needing 200 servers to run that model down to one server with a couple of FPGAs in it. So some of the returns on efficiency and the very high performance from FPGAs is pretty amazing.
That is fascinating. From 200 plus servers down to just one with a couple of chips.
Yeah,
That
5
is-
chips in that case.
Okay. Still, it's 2 orders of magnitude less in terms of resources, which
Right.
is quite fascinating.
Right.
So, sorry, I lost my chain of thought over there.
Well, one other thing on FPGAs, they come with flexibility as well. Fully custom chips are high risk and have really high upfront cost. You're easily $25 million into an ASIC spin, if not 100 million of total spend, easily. Whereas with FPGAs, you have a small upfront cost to get a hold of one of these things, but you don't have so much at risk. If you've got a bunch of code in this chip and there's a bug in it, it's an easy mistake. It's just like reflashing your firmware or just updating the software. Whereas with one of those custom written chips, literally the algorithm is written in stone. It's written in silicon.
Correct.
And if that's a mistake, these days, that's at least a $25 million mistake, which is pretty daunting. One of the reasons I went into FPGAs from having done ASIC design was because I was tired of the ulcers of taping that chip out and wondering if I just made a $25 million rock.
Oh boy,
I
that
can
would
quite
be
imagine.
really that's really measure twice, cut once.
Yeah, measure 10 times, cut once.
I have a follow-up question on the FPGAs. Now, I believe that we have FPGAs that are even available in setups like AWS.
Mhm.
What goes around the peripherals of the core chip? Is it, like you would imagine that if you had a custom chip, you have custom peripherals around it that
Mhm.
help support the logic inside the chip.
Mhm.
But when an FPGA is offered in a cloud-based system, what do you need around it to work with it, to test it, to deploy applications with it?
Well, from a hardware perspective, you'd have what you might typically expect. You have storage, you have networking. I can't speak specifically to the FPGA as a service instances that AWS deployed. I don't remember what parts they made public, what parts they don't. But networking, storage, in most FPGA systems, you have some kind of relatively modest powered processor nearby. But for the FPGA as a service deployments, you need libraries. Some companies can manage to staff up FPGA designers and do their own custom designs, and that certainly happens. But where a lot of the focus is building out those libraries.
Got it. Well, let's jump ahead to where you are at AMD. So, how did you land at AMD, and what do you do there, and what do you like doing there?
Well, I was running our flagship acceleration SoCs at Xilinx when AMD came in on Valentine's Day and showed us the love by acquiring Xilinx. And so far that's gone really great. The cultures are really compatible, and I saw an opportunity to step up and have a chance for a broader impact. It's something that usually drives me. And so I moved over here into our cloud division, where I run AMD's product marketing and business for our products in AWS.
And AMD has had quite a history with the products in the AWS ecosystem. I think they've been around for nearly 10 years, I'd like to say. And I think the overall the competition between AMD and Intel has kind of been off and on. How have you seen that journey? One, what made AMD take the plunge with AWS, and how do you guys look at the Intel race?
Well, first of all, I have tons of respect for Intel. They've done an awful lot for this industry. They were foundational to Silicon Valley becoming Silicon Valley in the first place. If I stand up and look out the window over here, I can see their headquarters. So I have a lot of respect for what Intel has accomplished, and particularly in the data center. I think one of the things that our CEO did, Lisa Su did, a number of years ago, probably starting in about 2015, and it's really around 2018 when I think the products that we had in AWS really started to have prescience, and we started to get a foothold in the data center. What's happened since then, from a business perspective, is incredible. Some of the data that I look at since 2017 or 18 shows me that AMD has acquired somewhere between 25 and 30% of the market share in public cloud and public data center. And that level of market share shift is just incredible.
Yeah.
And so I think generation after generation, what AMD has been focusing on is talking to our public cloud, our CSP provider partners, and understanding what do they need from their systems? What do they need from their chips? It's not always just about the chips themselves. In fact, usually it's about more than just the chips. And so understanding what do they need for their systems to be successful. But then I think AMD, and particularly here in the cloud, we share one of AWS's tenets of customer obsession. So one of the reasons I want to go to reInvent is to have a chance to talk to more customers than I could at any other time, to hear, what do you need? What are the pain points that you're experiencing, and what's holding you back? And that gives us an idea of where can we next invest in order to bring the best products to market for the customers. And I think each iteration that we've been through over the last 3 or 4 generations of EPYC processors, we've gotten better and better. And for Genoa, I think it's a real, AMD's arrived. We have the highest performance data center processor on the planet. Everything else is an alternative x86 processor now. And so that's what I'll be spending the next 12 to 18 months discussing as I go around the world.
I can quite imagine. Over the last 5 years, I think AMD has completely shocked the world with the kinds of performance improvements and I'd say performance and power, improvements that have kind of come to be. So tell us a little bit about what's been different about the fundamentals that have allowed AMD to be so good. And because there seemed to be some kind of a disruption that happened around the 2018, 2019 timeframe. Because, you didn't see such massive step function changes or step function improvements in performances and the way it was, blowing away the competition. What changed and what's fundamentally driving? Is there a technology difference? Is there a product lifecycle difference?
Mm-hmm. So good question, Rahul. And it's really a number of things. There are technology components. There's a strong partnership component, especially with the latest iteration of our products with AWS, with the Genoa-based processors. We worked really closely with AWS to tune the systems, particularly with respect to simultaneous multi-threading. So funny you should ask. So from the technology component, I've actually got one of our latest and greatest processors here.
Wow.
If you look at this chip, you can see there's multiple pieces of silicon in here. It looks like there's 5, but there's really 13 pieces of silicon here. So this is a Genoa 96 core processor. If you go to run on M7A, C7A, or R7A, this is the CPU that you're running on. And so AMD was really a first mover in the type of assembly technology that this chip comes with, you can see there's multiple pieces of silicon, whereas traditionally chips would be designed with a monolithic piece of silicon. So one giant piece of silicon, which is challenging because I don't want to get too deep down into the weeds of chip technology, but the defect density, you get so many chips per wafer, and there's always going to be defects. And if you have one defect, you're taking out a huge slice of your silicon. That ends up increasing cost because your unit costs go up. Whereas if you have much smaller slices, you have an effectively lower defect density. So it's a combination of the assembly technology, which you see here with this chiplet technology. It's also a combination of architecture. The EPYC architecture is really, really good. The way the caches are architected, as well as the amount of cache that's there. And then to step up another level and fast forward to the present, with the 7th generation Amazon EC2 instances built on EPYC processors, the Genoa processors, we decided to go with SMT off, which effectively gives each VM, each vCPU access to a full core without having to bump up against neighbors that might be running literally within the same CPU. And if we get into it, there's a tremendous performance uplift generationally from Milan to Genoa, what would be AMD's 3rd gen EPYC to our 4th gen EPYC, in terms of what you see coming out of the AWS instances. And a lot of that comes down to what we did with SMT this generation.
So that's a really neat, good point. I think we will get into that. Yeah, so SMT, or I guess the idea is initially like when you run HTOP on your computer and you see, okay, here's the amount of cores I have running. But then if you run either SMT or it's called hyper-threading, but the idea is that you can have one physical core that represents itself as 2 logical cores. And on the perspective of a day-to-day computer where you have lots of threads running, but they're not all busy at the same time, that model makes sense in terms of, yeah, if you're interacting with it, you got lots of programs running. But if you're doing something that's computational, you don't necessarily want that thing on because it's just switching context a lot, but you're not actually gaining any more transistors. And so with SMT off, I really like that idea for high performance computing. So with SMT off on the M7 or R7 or any of the 7A instances, one vCPU means one core. That's what you're saying?
Right.
One physical core.
Correct. And that unlocks an awful lot of power. And there's multiple reasons to have done that. One of which is through very high performance, and you see this particularly with the 7th gen instances from AMD at AWS, it's possible to unlock what I like to call performance-driven cost optimization. Let's rewind a year. Stephen Rahul, we got together last year at reInvent, and one of the AWS reInvent, and one of the most common theme last year, every partner, every customer, every single one of them came to say, hey, we're heading into economic uncertainty in the coming year. And so their top priority was cost optimization. And there's ways you can solve that with retail costs. With our last generation Milan instances, we were at 10% lower retail cost everywhere in the world except in India, where we're 45% lower retail cost versus the alternative x86 at equivalent or better performance. And I see that was very appealing. That was very useful to customers. We saw some good adoption. And so I was thinking, now with this performance that we're going to get out of Genoa, how else can we augment that besides just dropping the retail costs? How else can we provide a return to our customers? And with Genoa, you can really see it. Because the performance is so high, the total net job cost can be, and usually is on average, much lower than the alternative x86. If you run in half the time, even if your retail cost is a little bit higher, your net job cost is going to be lower.
I agree. We've done a bunch of benchmarks around these new Genoa processors, and they are absolutely mind-blowing. But if you can help us kind of understand a little better, especially for the audience, now, of course, we have a scenario where across the different chip types, you basically have a different metric or a way to measure the performance or costs? Because if you say one core on an Intel, that's different from one core on an AMD, which is different from one core on any other platform, maybe even Graviton. So how should we really think about measuring the cost of something that we are running? And because that's the bottom line today when we talk to customers, right? So can you put that in perspective for everyone? How should they start thinking about the AMD performance versus Intel's versus any other architecture?
I think there's really two ways to look at it. Traditionally, I think, and you guys might know better than I do because your cost optimization tool is in the customer's decision cycle probably more often than I am, particularly when it comes down to cost. But in my opinion, there's two fundamental different cost models that should be considered for workloads or applications that are performance or time bound. CPU performance is of the utmost importance. And for most of the applications, at least where I am in the cloud, for the on-prem folks, and especially for the high performance computing folks, they get down into the weeds of the processor technology a lot more than the cloud folks do. And so I would say for the cloud folks, they don't even have to necessarily worry about, do I get one vCPU per core? Is it two or more? I think oftentimes that doesn't necessarily yield the cost and the performance results that they need to care about. What they should look at is time to done, time to decision, and net job cost. So for performance and time bound applications, those should map very well to Genoa because it's very, very high performance, highest performing data center processor. But that doesn't cover all of the workloads. There's other kind of workloads and applications that are always on. Or maybe they're not CPU performance bound. Maybe they're waiting for storage or waiting for the network. And so in cases like that, it doesn't necessarily make sense to pay for the highest performing CPU. Really what you want to optimize for there is hourly cost. If a job is, say, there's a login server running somewhere that just has to sit around 24 hours a day, 7 days a week, 365 days per year, you can't do 24 hours a day any faster. It just has to run all that time. And so for those applications, it's really hourly cost that matters. And in a case like that, the CPU performance doesn't matter. Our Milan generation CPUs are really good at it, or in AWS speak, that would be their 6th generation instances. So yeah, so thank you for pulling up this visual. That would be their 6th generation instances. That's what we're looking at here on the right. And so here we're looking at M6A, which is the Milan instance, versus what would be Ice Lake. And if you just run that 24 hours a day, here we're seeing 5% higher performance at almost 15% lower cost, right?
Yeah.
And so that's effective. And I guess the one other thing I would say there is you don't always have consistent pricing around the world. For Milan in particular, we're 10% cheaper than the alternative x86 at same or better performance. However, for customers that are able to geo-shift their workloads, their applications to the India region, and particularly to Mumbai, the retail cost there is, the hourly cost is 45% lower than the alternative x86. And so your returns get even greater. And so I see a lot of software and dev people that are doing CI, CD types of development, or when they're going to do the massive and highly, very costly testing that they need to do before a production release or before a production deployment. If they shift that over to the Mumbai region, I mean, they save almost half the cost.
That's a
So that's how I
phenomenal. What
look at
is
it.
about that kind of a variance in is there something particular about India that the AMD price points are way lower?
Well, I'm a little reluctant to speak for AWS themselves, but there's a number of things. I think at the time that those instances were stood up and deployed, the overhead costs that were associated with spinning up and running instances over in that region were lower. I suspect there were governmental incentives. And then also at times, maybe India was a little bit underserviced in terms of the types of cloud data centers that we were deploying there. And so it was a way to build momentum to actually draw customers in. But I see an awful lot of geo-shifted deployments going over there, especially for development and test.
Got it.
That's a really great piece of advice to add, right? Is that compare, like check on the pricing. Like, I think we have this default behavior of, what's the price in US East 1, right? That's what I do, is all my relative prices are based on US East 1, just because that's kind of the most common one. But then you think, okay, there's actually some non-trivial differences amongst the regions. And so if you can shift from one to the other, that's great. So there's region variation, and then just kind of to summarize this one time, there's region variation and also generation variation. So it's not always pick the latest generation, because right now both the 6 and the 7, they serve different purposes, right? So as fast as you want to, if it's as fast as you want to go, you want to get it time bound, price performance, do the M7s or any of the 7As.
Yeah.
But then if it's, like you said,
Keep
a
alive
server
with
that just needs
AI.
to stay on the 6As, the Milan series.
Exactly.
Oh man,
So,
go ahead.
well, both of those generations are still really great for new designs, for new deployments. It just depends a little bit on the fundamental characteristics of your workload. And that's one thing. A lot of times I see customers, when they're trying to evaluate, oh, what do we do next? A lot of times it's just status quo. But if they do consider the instance cost, a lot of times they just look at the hourly cost, and that's what leads the decision. But I think my job for the next year will be help people understand that can be a short-sighted evaluation, because the performance gap has increased so much this generation for AMD's EPYC with the Genoa instances.
Got it. I'm going to push you on one other dimension of optimization, which is a lot more common. So the two scenarios that we spoke about were more around where you've already kind of optimized or right-sized for a particular workload, where the number of processors, the number of cores, or whatever that you're using, that's kind of been optimized already. The vast majority of AWS EC2 usage instance, we find, is severely underutilized. We were talking to Rick Cox from the AWS Compute Optimizer team, and he said the average across AWS is in single digits. That's the utilization, CPU utilization, that you see across all of AWS, right? So now when you've got a typical workload, and these are probably particularly true of dev and staging workloads more so than production. When you have those kind of workloads where you want to first downsize to just the right size that you need to perform the tasks that you're trying to accomplish, how should one think about the downsize? Because as you downsize, unfortunately, 4 different parameters change at the same time. One, it's not only the CPU cores that go down, the amount of memory that's associated with it also goes down. Next, the I/O profile for disks, that goes down, because the kind of bandwidth that's available to the disk, that goes down drastically as well as you go, half sizes in every step. Next is your network I/O. That's also going to start having an impact, because that shrinks down as well. So your instances are shrinking on 4 different dimensions. And so it becomes really difficult to figure out where you draw the line about how much you right size. Any tips on the performance associated with shrinking the number of cores? How does that have a different profile with AMD instances versus Intel?
I'm not sure about AMD versus Intel per se, but some of the performance hit that can come as you shrink down in instance sizes. It seems to me that from probably 4XL and maybe 8XL sizes, which is 16 and 32 vCPUs, it's somewhere around that instance size, as you're getting smaller, that the variability in the performance of those peripheral interfaces that you just mentioned, Rahul, can become a factor. And they're not always a factor, but it does vary over time. The first thing that I've seen, and this comes from a lot of benchmarking and a lot of workload characterization that AMD has been doing since all these instances launched. What I'm seeing come out of that data is somewhere around the 16 XL instance size. From that size and above, you tend to have the most consistency of performance, so the least variability, and the highest performance. So between 16, 24, and 32, we see a lot more consistency. But I would actually answer that in two ways. Number one, if customers are asking themselves that question, it's a little bit hard to have a one-size-fits-all answer to that because every workload is unique, as I'm sure you guys know.
Yeah.
And so I would say, come to us or come to your AMD rep. I have an awful lot of performance characterization information that can help customers figure out for their particular workload and their particular environment, how are their workloads going to run on the various instance types. So general purpose, memory optimized, or compute optimized. But also, I usually do a very wide spread of running benchmarks on all the instance sizes that I can or that are relevant. And so there's a programmatic way we can begin to answer that question. And then the next step I would say is, we have a lot of funding for proof of concept programs, or if customers are bringing new workloads into the cloud and they want to evaluate them on AMD. In some instances, we can help them through funding with credits to evaluate where are those workloads going to land best. So it's not a shot in the dark.
Got it. There's one other piece of recommendation that I'd give you from a CloudFix standpoint, which is instead of taking the big multi-step jump to say going from a 32 XL down to a XL, don't do a multi-step jump, go down one step at a time. And that way you understand where your bottlenecks might be a lot better. And you can take them, like wait 2 weeks every time you take one step down. That way you have enough data, you have enough of a profile of how your applications behave in a particular scenario or with a particular, instance type. And that'll help you gauge very quickly which one you should be on. And I think doing A/B testing is also a really neat, way of, you can always put a load balancer in front of your instances and have a pool of instances in your old type and the new type. And that way you mitigate the risks that are associated with trying out the new instance type. I think for a lot of scenarios, there's no alternative but to actually migrate your application to the new instance type and try and see what profile it follows.
That makes a lot of sense. And, CloudFix has kind of become the easy button for me in some ways, Rahul and Steven. I'm talking to customers and partners all the time, and they're looking to cost optimize. Maybe they've got some new workload that's come to the market that they didn't budget for last year when they fixed their budget. So a lot of times, the reason I wanted to partner with you guys, and we have these joint initiatives going, is so that when I come across those scenarios, I can say, hey, the easy button is to go talk to the CloudFix guys, because you do this on a daily basis.
I tweak that a tiny little bit. From a customer standpoint, I think what they care about most is it safe? So the easy for them actually translates internally for them as, is it safe to move from X to Y, whatever those two states might be? And so at CloudFix, we've kind of constantly worked towards making sure that these transitions are as safe as they possibly can be. We take a very risk-averse approach. And that brings up a really interesting question and segue for you, Mike, which is, talk to us about, is there a fundamental difference in the architecture or the way applications perform on Intel to AMD as they make that transition? We treat most of those transitions as safe for various different reasons. Could you talk to the audience a little bit about your perspective of the architecture, what happens to applications when they move from Intel-based instances to AMD. Why would you consider those as safe?
Well, good question. Thank you. I mean, the elephant in the room there is the ARM architecture. And so let me just preface my answer here with, for all the DevOps and developer folks out there, I don't mean to trivialize at all moving between platforms. But moving between x86 platforms, x86 from different vendors, is pretty straightforward. It's the same fundamental architecture. In many cases, it really just comes down to flipping a switch in the EC2 console. Again, not to trivialize it. In particular, for applications that haven't gone in to do processor or API specific optimizations. And that's a lot of them have not gone into that, which contributes to vendor lock-in. But even with that, I think migrating between Intel and AMD x86 platforms is pretty straightforward, especially if you compare it to moving to a different processor architecture like ARM. Now, I'm a strong believer that the more diverse our ecosystems are, the better the ecosystem is for it. Competition breeds innovation. It drives us to be better. I'm very averse to technology companies getting complacent and just resting on their laurels. That's not good for anyone. But if you're to compare that transition between x86 to x86 and x86 to ARM, the x86 transition is trivial by comparison. Some workloads migrate fairly well, and that's all fine and good, but others really don't. It could be a year of time of having teams of people work on the migration, and having to recode, having to refactor their code base. That's really, really non-trivial. And what I see is there's an awful lot of customers out there, especially more among the small and medium businesses that don't have some giant R&D budget and can't necessarily afford to carry a whole nother team just to port. I think the x86 transition is trivial by comparison to moving to a different processor. What about, do you guys have any insight into that? What am I missing any factors?
Yeah, I think they're just we had one specific kind of instructions in very, very niche workloads.
Mm-hmm.
I'm trying to remember the specific. It was. It'll come to me in a second. I'll bring it up. But for the vast majority of customers, there really isn't any difference between the Intels and the AMDs. Like, you don't need to recompile your applications. You don't need to modify the binaries. You should be able to just run the applications as is on an AMD instance. So from an effort standpoint, to mitigate any kind of other risks, the effort is minimal because you don't need to do anything with the binaries. You can just take the same binaries and deploy them. That's unfortunately not the case with ARM. With ARM, you have to go through the entire deployment cycle from build onwards. So you go through the compile, you create the build packages, and then you go ahead and deploy and hope that everything works, that you've pulled in all the ARM binaries or ARM dependencies instead of the Intel ones, and everything else continues to work perfectly within that setup.
And
so
it
it's a
could be
little
the
bit
case.
more of a channel on that. Sorry, go ahead.
Oh, and it could be the case that that your project is ready to move, but a dependency has a library that isn't maintained on ARM or not maintained in the same way. Whereas they said x86 to x86, especially with the Gen 7s, where even like the super HPC things like the AVX 512, they're all
AVX
there.
512 is the one.
Yeah. So with Gen 7, they both have it.
Right.
Correct. Yeah, with Gen 6, that was one of the missing pieces. And that was only for the very niche high-performance computing kind of applications where they were specifically making use of that. But now, even that's kind of gone away. So that's not a concern either.
And so a lot of our discussion so far has been sort of from the CPU up perspective. There's also a top-down perspective. There's some applications that simply don't run on ARM. SQL Server, last I checked, still doesn't run on ARM.
Correct.
And there's a number of applications like that. But nonetheless, I think it's great for the industry to have diversity in the ecosystem. That makes us all better. So I embrace and welcome the new processing architectures. I think it's great for the industry and for the customers.
Awesome. Why don't we take a 30-second break and we come back? Let's talk about well, first of all the instance types, the M7, the C7, and also the different industries where this is used. I would want to get into that. So let's take a 30-second break and we will be right back.
All right.
Some tools just find AWS cost savings and make you do all the work. Visualizing cost opportunities is great, but that's not enough. CloudFix, on the other hand, actually delivers those savings for you. And you don't need to worry because CloudFix is AWS recommended and easy to use. It's the only tool that fixes cost-saving opportunities and not just fines. It's the easiest way to save money on AWS. It's all 100% automatic and risk-free. And the best part of all, it works non-stop. Stop overspending on AWS and click on the button to start saving now.
All right, we are back. Before we jump into that, I just wanted to do a little bit of AMD nostalgia. So I was kind of reflecting a little bit. I'm going to put this on the screen. I think it's kind of cool. The first CPU that I bought for myself was this one, the AMD K62.
Wow.
And I remember I could still picture the ad it was in the local newspaper. I can picture the ad for Computer Stop magazine where they listed the CPUs and the prices. And so, see, this was 200 to 570 megahertz. I bought the 300 megahertz one. And looking at this 250 nanometer architecture.
Oh my God.
Right. So comparing to the EPYC, right? But I remember, so this, May 28th, 1998. Yeah. So it was the summer. So I was 13, saving up for that 300 megahertz K62. And that was like the first system I built myself. And now looking at like the EPYC, right, where the Gen 7, we were at 5 nanometer. Where it's like thinking from 250 nanometers to 5. That is such an enormous just leap in my lifetime. It's like saying, I don't know, cars have gone from horses to sports cars, right? It's an enormous leap.
Yeah, it's crazy. So how about this? I was just thinking while you were pointing that out. So if you were to take the processing power of that chip that you were just describing and carve out the silicon area that would be required for the same processing power from this chip, if you could get that little piece of silicon, it'd be so tiny. I think you could probably see it, but I bet you could swallow it and not even notice.
Yeah, it would just be a tiny little speck on that.
Yeah,
on that enormous. That's incredible.
Yeah. I remember I had a K62 also, but that was my second or third machine, I think, that I had configured and hand built by then. But yeah, we've come such a long way. I still remember the days of megahertz being the standard. My first machine was 33 megahertz it was a XT, not even an AT instance. And we've come a really, really long way. Before we jump into the industries, one question for you, Mike.
Yeah.
So somewhere down the line, we seem to have hit the 5 gigahertz upper limit on the kind of clock speeds that you can achieve. Mm-hmm. What's the physics behind those limitations? Like what prevents us from going faster in clock speed? And as a result, I think we've gone down with having multiple cores. That seems to be an easier way to scale. But tell us a little bit about the physics behind that. Like what prevents us from going to higher clock speeds?
Okay, so I am not a fab expert, so I'm going to be speaking with kind of topical understanding of what's going on here. But there's a couple of things. If you think of chip fabrication technology, it still is, but less nowadays than it was back when that x86 you were showing there, Stephen. It still is fundamentally screen printing. It's a lot more fancy now than it was back in the day, But we've gotten to the point where the little features that we're etching on the chip there are so small that they're smaller than the wavelength or the amplitude of the light that we can use for screen printing. So basically they take a screen with the circuit all sketched out, and there's basically holes wherever they want to have a conductor or a semiconductor laid down. They shine light through this screen, it hits the silicon, and that's what they're able to deposit various materials around. Let's just say it's copper for conduction, for sake of argument. We've gotten to the point where the features that need to be etched are smaller than the amplitude of the light, or smaller than the wavelength of the light. And so they have to play some really fancy tricks in order to be able to etch those features. And so, that has an impact on the density of transceivers, the density of compute elements that we can get onto a chip. And it also starts to have an impact on how quickly that signals can propagate. Those signals are propagating at roughly the speed of light, the speed of electricity versus some resistance. As those features get smaller and smaller, there's higher resistance. If you think of a garden hose versus a straw, it's a lot harder to get a high volume of water through a straw versus a fire hose, say. And so that's one of the things that we're facing. But Moore's law, some will argue Moore's law lasted for a long time. Some would say Moore's law is dead, or where we're doubling the number of transistors every 1.5 to 2 years and maybe cutting the power by 50%. Some would say Moore's law is dead. Some would say it's asymptotically approaching its limit. But I think, that just means we need to look at a different kind of innovation rather than trying to solve it. How would I say? Rather than a brute force solution to the problem, there's other elegant ways to solve it. One of the ways that AMD, and particularly Xilinx, has been solving that challenge is through what we call heterogeneous integration, which means, sometimes you integrate a special purpose component, say for the PCIe interface. You have specialized silicon just to run that, and that's separate from your general compute. Do you have any thoughts on that? Are you guys deep?
I guess what you're saying is
technology?
So even though the speed is somewhat plateauing, we're getting gains in other areas, right? In terms of architecture, in terms of instruction sets, special purpose, I guess pieces of the chip that can do encoding or decoding. So in terms of what an actual chip can do, that's better than ever, and there's plenty of room for innovation in there. It's just not all going to come from raw clock speed, and it's not going to come from there might be a 3 nanometer process, but I think, like you said, at some point you hit the physical limitation of how close can 2 electrons be without getting that signal mixed up.
Right. And there's other ways to solve those problems, like with way more local cache, really tightly coupled to all the CPUs that are within a design. I think we need to look at other ways to innovate besides just the brute force method of trying to crank up the clock speed.
Makes a lot of sense. Okay, sorry for derailing the topic, but I was just very curious about this. As I was thinking about where we've come from and where we are headed.
It's all good.
One of the things that got my attention was that we kind of plateaued on those speeds. Anyway, sorry. Stephen, you wanted to talk about
which is what so what industries are using, or like what kind of adoption are you seeing with the Gen 7s, and what industries are using it, and what's important to them?
So I'm going to start with what kind of adoption are we seeing, and if I forget, remind me of the industry question. So to set the kind of backdrop, how quick of an adoption are we seeing? I'm going to take one step further back and talk a little bit about how quickly were these deployed. So previous generations, I'll take the Milan generation, 6th generation at AWS, for instance. AWS deployed 4 different instance types. There's the C for compute, there's the M for general purpose, There's the R for memory optimized, and then there's also the HPC, high performance computing optimized. Last generation with Milan, or AWS's 6th gen, that took about a year and a half. With Genoa, that pace has changed dramatically. Where most of my summer went is over this summer. Over the course of 2 months, AWS rolled out all those 4 instances in the space of 2 months. And so really, really fast rollout. I think AWS can speak to why did they do that. I like to think it's because they saw the promise of the performance returns of not only the EPYC processors, but the platforms that they designed around them, and they just wanted to get them to market. That's not an official AWS stance. That's my opinion. And so they rolled those out 7 times faster than the previous generation. And the indications that we're seeing so far is that the ramp on AMD powered instances, on Genoa powered instances, is faster than we've ever seen before. And so, I'm like a kid in Candyland this year. Being in charge of product, it's all sunshine and roses at the moment. So really fast adoption. And then second part of your question is what industries? Is that right, Stephen?
Yeah.
So all sorts of industries. And that's one of the fascinating things about working in cloud. I was talking earlier about in my career trajectory, I wanted to have a broader impact and work on more types of things. And the scope and the breadth of what cloud computing is doing for the world is, I think it's the biggest scope of any industry I'm aware of. And so I see a lot of adoption from financial services, particularly for general IT, where there's a lot of overhead spend. Same thing with manufacturing and healthcare. I think those are the 3 most vibrant industries that I'm seeing: FSI, manufacturing, healthcare. There's an awful lot of technical and high performance computing. I think AMD has had a really strong position in HPC for a long time, so no surprise that we continue to see that. And honestly, pretty much every other industry. So really broad and very fast adoption.
And then what are the 7th gen instance types?
Let's see. So M7A is the general purpose instance type. C7A is for compute optimized. It's compute optimized for compute intensive applications. R7A is memory optimized. So for applications that are really hammering on the local memory, R7A can be really good. And then for really tightly coupled high performance workloads, there's HPC 7A. And historically, I think mostly we've seen the HPC instances be deployed by, typical HPC wonks, folks that really get down into the weeds in terms of how is their workload running on the processor and optimize everything that they can out of it. But something that is, I guess, a little bit of a pleasant surprise is I'm starting to see some other industries take advantage of the HPC instance types, particularly in financial services for things like quantitative analysis and risk modeling. And I wonder if can you catch the cheat code from M7A, C7A, R7A, HPC 7A? How do you know if it's an AMD instance?
There you go. That's great. Add the well here. I've got my tribute to that in my my 3D printed instance type here. So this is
there you go.
The
A.
That's the A.
Go
Ding,
for
ding,
that
ding,
A.
ding.
Correct.
So you printed that.
Yeah. So I grabbed the
That's cool.
SVG of an Amazon logo and then printed this out. This is a 2-layer print. I've got a bigger one that I'm experimenting with, but I had a limit to how big the print bed is. Let's see. So here's the 7A. So this will be a multi-part print. I just need to glue it up together and print a backer for it. But I'll have a big M7A display.
If you're going to be at reInvent, any one of you, if you're going to be at reInvent, please come by the CloudFix booth, where we're going to have AMD folks there, and at the AMD booth, which always promises to be a huge, big, fun affair. And we at CloudFix are also going to be there, and you can get to see Stephen's prints over there that he's going to carry all the way to Vegas as well.
My printer will be staying warm until Sunday. Well, Mike,
Maybe we
what are
can
your?
convince Steven to print one of your logos too. That'd be pretty cool. You're on the hook now, Steven.
Well, I just got some blue-green filament because we have this blue-green gradient logo, and so it just arrived yesterday. So I'm gonna try some experiments later today.
Yeah, but this
Awesome.
is actually a good segue to one other aspect that I wanted to talk about. So I wanted to state for everyone out there, moving from the Intel instances over to the AMD ones is relatively straightforward. For the most part, CloudFix makes it really easy. We have a finder fixer that with one click can get you to those get you across those instances very, very quickly, and you can do it yourself. The only caveat is if you're migrating across generations, let's say you're migrating from a 6th generation over to 7th, then as long as you are on an Amazon Linux instance or one of those AMIs, again, it's very, very straightforward, really simple, one click, switch over. The likelihood of something going wrong is abysmally small. The only one where you have to be particularly careful about is if you custom built an AMI and you are migrating across generations, then you just need to make sure that the AMD drivers are installed on your AMI so that everything can work seamlessly. And that's literally the only check. It's a super easy, straightforward check and fix if you don't have them installed, and you can migrate them. So from effort to achieving, cost efficiency and benefits, it is as minimal as it gets out there. So if you are on an Intel instance, please do explore the mechanism of taking those instances and moving them over to AMD. It is really simple, really straightforward, and the latest generation of the AMDs, so the Genoa ones, are absolutely fabulous. So you should try them out for sure.
And just relative to add what you said, looking at for example, the M7As to the M7, their other equivalents. The A's size for size are a little bit more expensive, but that's not the end of the story. They get a lot more done given that size. So you're going to need a smaller size, right? So you can say, okay, I've got a 16x large. I'll swap it over to a 16x large. But then you think, wait, I've got a lot more headroom now. I can bump down to a 12x large or an 8x large.
Right.
Correct.
So that's that kind of two-step move.
Exactly.
So I've got the math based on a bunch of benchmarks and the instance pricing that we're aware of today. If anyone's interested in diving into the details there, on average, you're going to get 37% lower cost at double the performance by going with the AMD instances. If you want to go into the math and how do we come to these conclusions and whatever, if you're coming to reInvent, swing by, let's have a chat. I can show you the specific math of how we came to those conclusions. If you're not coming to reInvent, reach out to your AMD rep or your AMD salesperson. We've got an awful lot of data to back this up, and you stand to benefit in multiple ways. For the technical folks, especially for the folks that are running large compute intensive workloads, you get time to decision and time to done much faster. And then the flip side of that is because it runs so much faster, if you look at the total job cost, it runs a lot cheaper. And I see a lot of people taking advantage of those savings. They almost always get reinvested, but say generative AI, this isn't something that was planned in the budget last year when this year's budgets got fixed. And so if you need to carve out, so here what we're showing is table on the left, we run way higher performance, table top right. So we run in a much smaller footprint, table bottom right, hence we cost less. And if you take advantage of that cost savings, you can carve out existing cloud spend to go invest in new workloads or capacity expansion, new workloads like Gen AI, which most people didn't plan for.
Correct. And this is the reality, I think, across all organizations today. Over the last 6 to 8 months, pretty much every CTO, CIO that I have spoken to have told me explicitly that there is a board level mandate across those organizations to do something new, innovative with AI. Mm-hmm. And almost none of these organizations ever budgeted anything for that eventuality Things have moved so rapidly and so quickly in that field that everyone is trying to play catch up. And if you've not budgeted for it, then you have to carve out the budget for it from somewhere else. And there's no better time, no better place to carve this out than with the kind of processors you're using. They're big savings, like you just saw on those charts. You can start saving that money, carve it out of your budget, and then apply them to places like doing new generative AI projects.
Or expanding capacity. Yeah, instead of cutting budget to existing programs, which probably very fully need the budget there, instead of cutting those back to reinvest, leave them go. Just cost optimize by flipping the switch to AMD, and then you can have nearly 40% of your cloud spend freed up to go invest in those novel new workloads.
Absolutely. I think there's just so much gain to be had. I can say just looking at all of the data that exists with us across all of our customers, I can say without a doubt that there is at least a 40 to 50% room in terms of new efficiencies. So, there's tons of gains to be had. Use those gains to invest and do more with innovation.
Do more with less.
Exactly. Okay.
Well, we're at the end of the hour. I just wanted to ask one other question. Well, what does your 2024 look like? And also, what's your Thanksgiving looking like?
Well, 2024, given the major performance and price performance or performance per dollar uplift and the energy efficiency associated with that, I'm super excited and optimistic about 2024. I'll be traveling the world to help educate customers and partners on the real legit value that running on EPYC Genoa powered platforms in AWS can bring to customers and their businesses. I'm also really excited to go. I'll be traveling through the European Union, a couple of times. I'm really interested to see firsthand their take on the energy efficiency, because I'm seeing the most demand for energy efficiency coming out there. And that's not something that we touched on explicitly, but the EPYC Genoa is also leading in terms of energy efficiency. So I'm really excited to go and talk to those customers and see what are the guidelines that they're trying to operate within, and how can we help them solve very real global problems today by bringing a much more efficient processor to their cloud. And as far as Thanksgiving goes, Stephen, I'm not a traditionalist as it comes to that. I love the tradition of Thanksgiving. It's my favorite holiday of the year, but I don't like turkey. Maybe I can eat it one dinner, but then having it sitting around for the next month or month and a half I'm not a fan, and I end up throwing this stuff out. So I roast a goose for Thanksgiving. We usually host Thanksgiving. I'll be roasting a goose. I just picked it up last night. It looks really nice. Can't wait to pop it in the oven.
Awesome. I hope it comes out well.
Thank you.
What are plans at your end, Stephen?
Let's see. I'm going to attempt some smoked turkey legs. So I got to get them brining tomorrow, and then I'll be standing outside supervising the grill with my brothers-in-law and my brother, and just have a nice, relaxing time with my family. I think we're hosting this year with all my siblings and parents, so that'll be really fun.
That is awesome. That sounds like a lot of fun.
Make your siblings do the cleanup. That shouldn't be on you.
I'll give that a shot. I'm the oldest, so we'll see. They're pretty good.
I hope all of you have a wonderful Thanksgiving, and we will see you all next week in Vegas at reInvent.
Yeah.
All right.
See you next week.
Bye.
See you, everyone.
All right.
Bye-bye.
Take care, everyone.
Some tools just find AWS cost savings and make you do all the work. Visualizing cost opportunities is great, but that's not enough. CloudFix, on the other hand, actually delivers those savings for you. And you don't need to worry because CloudFix fixers are AWS recommended and easy to use. It's the only tool that fixes cost savings opportunities and doesn't just find them. It's the easiest way to save money on AWS. It's all 100% automatic and risk-free. And the best part is that it works non-stop. See for yourself. Click on the button to get a free demonstration of CloudFix and stop over